Hello and welcome to a training on modeling, doing hydrologic modeling for porous pavements. My name is Maria Cahill, and I'd show you a picture of me from my computer cam, but I work at home and I'm not in my pajamas, but my hair is pretty messy, so you'll have to go find a picture of me somewhere else. But I'm happy to be here with you today. I have my own business. It's called Green Girl Land Development Solutions. It's a sole proprietorship, woman-owned business located in Portland, Oregon. And I was hired by Oregon State University Extension, OSU Extension, to work with small municipalities in the lower to mid Willamette Valley. So that's an area in the Cascadia bioregion. And it's significant because this model is developed specifically for Western Oregon, basically, but it could also apply to Western Washington and some of Vancouver, BC, and some of Northern California. So just a little caveat there, but I do have other models with different rainfall distributions that would apply to other places. So if you're interested in those, you can always contact me, or if you have any questions about this presentation, you can contact me by email at greengirl@greengirlpdx.com, or you can call me at 503-334-8634. So this is the first slide of a PowerPoint presentation, a training that I gave on February 28th, 2012 on porous pavements to a number of different small jurisdictions. What we mean by small jurisdictions is that they are under the Phase 2 NPDES permitting requirements. So this is kind of a technical training, and I'm not going to go into a whole bunch of detail about what that is, but you can Google it and find out what a Phase 2 community is. And our communities are smaller than that. Sometimes they're just 1,000 people. The cutoff for a Phase 2 community is 10,000 people. There are other criteria as well. But all of our communities are trying to use low-impact development practices like porous pavement, like rain gardens, like green roofs, to help them meet their TMDLs, so their total maximum daily load requirements. Every city, regardless of whether or not they fall into the higher, the more stringent criteria of a Phase 2 or a Phase 1 community, still has TMDLs for their watershed that they have to meet. And that's what our communities are trying to do. So this PowerPoint presentation has a whole bunch of information about design and construction and maintenance and other things, but we're just going to do, and so I encourage you to take a look at this PowerPoint presentation in its entirety, and you can do that. You can access that and a whole bunch of other information by Googling OSU Stormwater Solutions, and the first thing that pops up is extensionoregon.edu Stormwater, and it'll take you to here. And then we are the LID Academy, and you can go to here, Porous Pavement Resources, and you can find the calculator there along with a whole bunch of other things that we gave as handouts for the cities, or you can go down to Design Your Site, and you'll see the Porous Pavement Hydrologic Calculator here. And so you can see here there are some design criteria. There are two different design criteria when we're designing porous pavement. So we have a hydrologic design and a structural design, and then whatever the base rock turns out to be that's deepest to meet the traffic loads and the amount of stormwater that we're supposed to infiltrate, the deepest base rock is supposed to be your base rock depth. And that's basically what we're looking for when we're doing our design, when we're doing the hydrologic design. And that's all we're going to deal with now. You'll need a geotechnical engineer to give you a recommendation for the traffic loads, for the setting, for the soils, the native soils in a wet, uncompacted condition, to find out what the base rock should be to hold your loads and do the structural design. But you can see here, Porous Pavement Hydrologic Calculator. There's some information about that. You can download two different calculators. So I'm going to break this talk up into the simple Porous Pavement Hydrologic Design Calculator, and then there'll be another movie that you can watch, another tutorial on as porous pavement as a substitute for detention in agencies that haven't quite seen the light yet about porous pavement, but do have a detention requirement and want to understand and feel comfortable that porous pavement is going to meet their detention requirements. In fact, porous pavement will exceed their detention requirements quite easily in most cases. So you can see here there's a whole bunch of information about the model, and we're going to get a tour of that right now. But at any rate, there's a whole bunch of other information here too. Fact sheets and planning information, decisions. We got some cool decision trees like the porous pavement siting criteria. So I encourage you to come here and take a look at this. Okay. Slide 84 is where we start our description of the simple hydrologic design case study. So we're going to take one of the cities that we're working with, the city of Turner, who is looking at porous pavement. We're going to assume that all stormwater must be kept on site and that they want to protect from stream scouring. They have a downstream waterway that's receiving too much runoff and for too long, and so it's getting scoured, and they're going to infiltrate the 2-year design storm. This is the ideal. Watersheds vary. So a watershed might be the shape of a channel, and whether or not it's scoured might be based on experiencing the 1.5 year or 18-month design storm, 24-hour design storm, and it might go up to the 2.5 year 2.5 year 24-hour design storm. But the 2-year design storm is really easy to find from NOAA isopluvial maps, which we're going to learn more about in a minute. So this is a good rule of thumb when you haven't done a really in-depth study of your watershed. So let's start with the 2-year design storm. We're going to assume that it's hydraulically isolated. So that means that there's no runoff coming from the surface of an impervious area draining to a porous area. That's a clogging problem anyway, and a maintenance problem. It's done for a lot of different reasons in a lot of different places, but if you're looking for a low maintenance pavement that's not going to clog prematurely, you should be looking at doing the whole road section as porous pavement. And this is done in many places. It's safe to do. Turning radiuses and things like that are a function, or not turning radiuses, sorry, turning movements that might spoil the pavement or damage it in some way, and traffic speeds. You know, a lot of people have concerns about those two different things, and often that's why we don't have pavements that are hydraulically isolated. Those can all be addressed in the specifications. So there are ways to make the pavements strong enough to handle those situations, and you shouldn't be afraid of just doing an entire road or an entire parking lot in the porous pavement and giving your client a really easy to maintain, very unlikely to clog if you follow the other design guidance that's in this PowerPoint presentation, pavement. The other criteria that we're going to assume is that it's not in a flooded area, because flooded areas tend to dump a lot of mud onto the surface of wherever they flood, and that mud could clog the surface. So we're also going to assume, so here's a little picture of the post-developed model. That is we're just looking at the simple model to find out what depth of storage rock we need to infiltrate what depth of rainfall. So I know this looks like Greek, but I'm just giving you a quick tour. We're going to go through these one by one. But the model itself is a model in Excel. It's a Santa Barbara Urban Hydrograph Type 1A rainfall distribution. I have porous pavement models for other distributions. As I said, rainfall distributions Type 2, and I think I have Type 1. So contact me if you want those, but this particular contract is for Western Oregon, and Western Washington actually will have a Type 1A as well, but my contract is for Western Oregon. So that's why we're getting a tour of the Type 1A 24-hour storm. And this is this particular one, actually the screenshot is to assess flood storm attenuation. That's the detention one. So But the user inputs and the calculated values for ponding are all the same for the simple. And that's where we start to look at the detention ones. So we have our user inputs, which are in yellow. The stuff in white are things that you may not need to change. The stuff in purple is whether or not you've met an important criteria. Then we've got some calculated values, ponding, calculated values. We'll look at that in the next video for 25-year storm attenuation. We've got other calculated values that engineering geeks like to look at, and then the actual hydrograph is in this Excel sheet, and it's just right below our user inputs. And I showed you a little thing on the website where you could get all the information you could possibly want about all these different things here. All these different columns are described in detail. What is embedded in the what the information means, and well, these are the user inputs. But let's see. There's post-developed Santa Barbara hydrograph for both simple and detention porous pavement calculators. You should never have to edit any of this. So column 1, column 2, what the calculation is that's embedded in that Excel sheet, and what it means, and how to interpret that meaning. All right, so let's go back to our PowerPoint presentation. And this model is based on work that Steve Fancher did for the city of Portland back in 2000 something, and he was really he's a really smart guy. What he did was he uses the rational method, which is a conservative way to generate peak flow for a site. So usually it's just used on a big site, well, on any size site actually, and it's used to generate one single peak flow for a 24-hour storm coming off of that site. But what he did is he said, well, I'm going to generate for every 10 minutes, for every 10 minutes, I'm going to generate a peak flow, and I'm going to generate that peak flow based on the shape of the Santa Barbara urban hydrograph. So we have our rainfall depth that's changing here and looks like the Santa Barbara urban hydrograph type 1A storm, and then he's generating rainfall intensity, and from that the inflow rate. That's the flow rate, the peak flow that's being generated by the rational method, Q equals CIA. And we'll see some of the numbers that we need for that Q equals CIA. Q is the flow rate. As we go through the user inputs. And this model goes out to 72 hours now. When I first designed this PowerPoint presentation, it only went out to 30 hours because usually facilities have to empty out in 30 hours. But there's so much storage in the rock with a type 1A storm that I think that might not be completely necessary. So you'll see that in the other detention discussion that I do. But anyway, for the city of Turner, let's assume that they do either pervious concrete or porous asphalt. You can also use, these are standard details that you'll find out on the OSU Stormwater Solutions website, by the way, along with a lot of other information, notes and specifications, you know, what the gradation of this rock is and things like that. In the public right-of-way, it's usually going to be pervious concrete or porous asphalt. So the first thing we want to do is enter our rainfall depth. Let's go to our user inputs and find out what our rainfall depth is. We already said we want to use the 2-year 24-hour storm. So just a little side note about this presentation is I wanted to make this readable later as well, so I just embedded all the text that I wanted to say into this. I encourage you, so it's right there coming up, and I've already said this point, so I'm just going to move on, but you'll see that text flashing by. I encourage you to go to the PowerPoint presentation under the LID Academy Porous Pavement Resources and read through these if you want to too, just to have another way of learning the material. Okay, so enter the rainfall depth. So for the city of Turner, I went out onto the web and I found the NOAA isopluvial map. So an isopluvial map is a contour map of rainfall data. So all of this line here is predicted to have a 2-year frequency storm of 2.5 inches. So we see a 25 here. This map is in tenths of an inch. So it's 2.5 inches. City of Turner, to protect their storms, to protect their streams, needs 2.5 inches. So that's what we enter in our post-developed 24-hour rainfall depth, 2.5 inches. And then our pavement area, I just picked, for this example, I just picked any old area. It's a big area because I'm feeling excited about porous pavement, and I think you will too, and you'll want to put it in a really big area. So I just picked a really big number. It really doesn't matter what that number is. It should be the size of your pavement area. So we're just going to assume it's 115,000 square feet. Okay? And the storage rock area is going to be the same as the pavement area. Storage rock is the base rock below below the pavement surface, below the asphalt or the concrete surface. So that's going to be, for hydraulically isolated areas, that's always going to be the same as the pavement area. And the drainage area runoff coefficient. So this is the C in the rational method. This is, Q equals CIA. Well, maybe you don't know, but you can Google the rational method, or even just Google Q equals CIA, and you'll get some information about that. So this is the C. This is the runoff coefficient. It is basically saying that 98% of the rainfall that hits the pavement or hits a surface is going to run off. That's the theory of the rational method. In real life, porous pavement doesn't have any runoff. The rainfall passes right through the porous surface, right through the open graded porous rock, right through the wet uncompacted subgrade, and it just keeps going and makes its way out to the stream whenever it gets there, through the pores in the soil. So I just assume that 8% of the rainfall that hits the pavement is going to make it into the rock below. So this is a proxy for what's happening. We don't have runoff. We're managing rainfall with porous pavements, but we're using this model as a way to say, okay, 98% of the rain that's hitting the pavement is going down into the base rock. And there's about 2% that probably gets caught on the rough surfaces of the top of the pavement and evaporates back up. Probably a reasonable assumption. Your civil engineer might say that this is 0.9. That's up to you. You can change this. It's white because I think you don't need to change it if you don't know what it means, and this is a conservative assumption. So, native soil design infiltration rate. So you only want to test, you only want to enter a number in here when you have tested your soil. And I have a whole bunch of information about testing your native soil, and we can just go over that really briefly. There's information in here. I encourage you to look for it, but don't rely on the NRCS Web Soil Survey. That survey was done for agriculture. It was done at a much larger scale than the site scale, and if you're going there and finding the hydraulic conductivity of your soil class, you are not finding the information that's actually that you actually need to fill this piece of information in. So only enter this after you've tested the soil where you're going to put the porous pavement in. And how do you do that? Well, let's say we have this proposed condition where we have the existing grade. The porous pavement is going to go into a cut in that area. So it's we know that it's going to infiltrate. We don't want to put porous pavement on fill. That would change the storage rock and porous pavement area those two numbers would be different if you put any of this on fill. And sometimes we will put it on fill just for constructability, and we'll still have, we might just have to thicken the base rock a little bit. But let's assume here that we're all in cut. The bottom of the pavement is in cut, and we've got our native uncompacted subgrade, our pavement section here, our finished grade there. So let's just simplify this picture a little bit. We've got our porous pavement section, existing grade. This is what it looks like when we go out to test it. So we have to know a little bit about, it's helpful to know a little bit about where the pavement's going to go in terms of site planning. You want to do this early in the site planning, but but you want to you don't want to do it so early that you don't know where the pavement's going to go or how deep it might be. So you take a guess at that from experience, and this is why you work with a civil engineer and a geotechnical engineer. So basically, I'm not going to go through this whole thing, but you basically prepare the hole. You want to set a pin in the elevation, set a pin in the hole. It's just a post hole digger. You just get a post hole digger out there and you go down to the bottom of wherever the facility is going to be and put a pin in to the top of the ponding area that you think it is. So I'm going to assume that I have 12 inches of ponding area, but I might put a pin in at 6 inches, and you'll see why later. But you don't want to pond up too much, because the hydraulic head of the water can push it out faster than it will actually go when you have a pavement installed. So that's important. You fill it up. So here's all the information that you'll need to test your soil. But basically, you just pour water in there and you let it empty out, and you do that again, and you let it empty out, and you do that again, and you let it empty out. Each time as you're letting it empty out, you're measuring in irregular intervals how long, and it's kind of regular, but it's never going to be exactly regular, and so it doesn't have to be exactly regular intervals, because you're going to do a little bit of math at the end. But basically, you want to find out how long it takes for that water to drop from the pin, and that's inches per hour, right? So that's an infiltration rate that we're looking for, and you just keep doing that. You do that 3 times. Fill it up, let it empty, fill it up, let it empty, fill it up, let it empty. And when you're all done, you have you take the lowest number, the lowest and slowest average infiltration rate that you find, and you use that. And then you over excavate the pavement to make sure that the pavement area, to make sure that bedrock is at least 2 feet below the pavement, and the high groundwater table is at least 3 feet below the pavement. And the porous pavement siting criteria decision tree on the OSU Extension Stormwater Solutions website will help you to make sure that your pavement is that your site, is suitable for porous pavement before you even get into this. So we're assuming that you've already answered that question and you know. But you might be in the super early planning stages and you might not know. But that's an important criteria. So what about pre-soaking? La 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 la. There's some comments on pre-soaking. So we went through this. Let's theoretically say, for the City of Turner example, we went through this infiltration testing, and we found that the native soil design infiltration rate is 0.1 inches per hour. That was the lowest value that we found over 3 sets of water drops. So that's probably much lower than you're used to seeing as a criteria for porous pavement. But we're going to see here the rock doesn't even fill up with a type 1A storm distribution. Let me just make a little comment about that. The type 1A storm distribution is it's here in Western Oregon, we get 9 months of rain, and we get it in very small amounts. So it could be misting. It might not even feel like, it might not even be wet standing out in it for an hour or so. It can be, the mist can be so fine. So it's a very soft rain that happens over a long period of time during the year. And for example, in Portland, we get 37 inches of rain a year, and we get it over 9 months in this type 1A pattern. Now, where I was born in Pennsylvania, they actually get more rainfall per year. They get 45 inches of rainfall per year in the Piedmont Plateau, but they get it in these giant thunderstorms, just pouring down buckets in 3 months in the summer. So totally different rainfall pattern, and that's what the rainfall distribution means. So we can go down to a really low infiltration rate here in our type 1A storm because of that rainfall pattern. That may not be true in a type 2 or a type 1 rainfall distribution. So on step 6, enter the storage rock. That's the base rock, or the depth of rock that we're going to need for structural stability and to infiltrate our stormwater. So the depth of our storage rock, I'm just going to try 12 inches off the top of my head because I have a little bit of experience in this, and in porous asphalt projects, I've seen recommendations for 3 inches of asphalt over 12 inches of base rock. And in porous concrete projects, I've seen 6 inches of porous concrete over 6 inches of base rock. And since 12 inches is bigger than 6 inches, I'm going to try 12 inches first and just see how it goes. So the storage rock is a very particular kind of rock. It's called open graded, which means that we just have the big rocks in a gradation of rock. All of the rocks are about the same size. They're either 1 to 1.5 inch rock or 3-inch rock. 3-inch ballast rock is very durable. But basically the idea is that regardless of the diameter, the void ratio is very similar. It's usually around 40% void ratio. So when all the rocks are about the same size. Now, in conventional pavements, we have what's called well graded, and that means that there's sort of an even distribution over the gradation or diameters of the rocks, where the big rocks are mixed in with a whole bunch of little fines, and all the way in between that stuff too might have, it's just from the big rocks all the way down to the little rocks. There's a portion of that in the mix of rock, and it's the little rocks that let us compact the base rock, but it's the big rocks that give us our structural stability. So we don't want to compact our porous pavement. And this is why it's so important to get a pavement section recommendation from a geotechnical engineer, because we are going to be just lightly compacting those big rocks just to lock them together. And we're not going to have any fine rocks that are going to make it highly compactable. And this is where the water is going to be stored until it can infiltrate. So 40% void ratio, that's what that means. And I made it white because you probably could get away with not changing this. But there are some open graded rocks which might go down to 30%. And this is a physical property that's very easy to test yourself. Oops, that's my phone. I'm going to get back to her. And turn my phone down. Sorry about that. So the void ratio is something that you can get from your rock supplier, okay? So in the demonstration that I gave of the training, I did a little example of how to test the void ratio for yourself, but we're just going to move on. So step 8, enter the overflow elevation above the bottom of the storage rock. So I really recommend having some sort of overflow structure where you can have the large storms have them be able to get out of the pavement section. But there are some pavements designed out there that don't have any sort of overflow structure. So the overflow structure can be, sometimes it's just well, we'll get to this. So I'm gonna just say for simplicity that we don't right now have an overflow structure. So that means that the outflow elevation above the bottom of the storage rock is equal to the depth of the storage rock. It's 12 inches. So that's where we might be storing water. And in this arrangement, water has access to the entire 12 inches. If I put an overflow structure in and just limited the depth of ponding to 6 inches in the way I engineered that system, then I would be putting 6 inches in this value. But for right now, I'm just trying to get a feel for how much how much depth of rock is really needed to infiltrate my 2-year storm, which is the 2.5 inch storm. So I'm just going to make these equal for right now. And determining the ponding depth. So here's a little description of the outflow elevation. So ponding depth here is equal to the base rock depth when the pavement is flat. You can see. But then when we're on slope sites, this we really don't have a ponding depth. The ponding depth isn't this anymore. It's this here, right? And I really don't know what you would put in there in a model. This situation doesn't apply to my model that I'm giving you. So if you have this situation, don't use this model. Don't use this Excel sheet to figure this out, because I don't know how to figure it out. So engineers and engineering designers like myself tend to be a little bit more conservative, and they say, okay, well, we're going to flatten. If it's a sloped site, that's okay, but we are going to flatten this out so that water ponds, and so the ponding depth is now this point here. So these are all examples without a control structure, which, as I said, I don't recommend. And I'm sorry, I don't know where my curb went here, but there's a little curb there to make sure that the landscape area up here doesn't come down into here. Okay, so that's my text for that. So what if we want to have a perforated pipe at the bottom to have overflow control? Well, then we have no ponding depth. No water is going to pond in this and infiltrate into the native subgrade, because we've given it a much easier place to go. We've given it that perforated pipe, and it's going to flow right out of that perforated. It's going to work its way to the rock and right out that perforated pipe, and then right out to a non-perf pipe. And basically, you've wasted a whole bunch of money when you have this, because it's not really going to work very well. Now, some people say, well, okay, if you want to raise, why don't we just raise this pipe up, and then we'll have some ponding depth, right? So it would pond anywhere below that pipe and then flow out the pipe. Well, because all pipes, this pipe is probably a plastic pipe because it's perforated, and all plastic pipes, in fact, all pipes in general, need some cover to protect them from damage, to protect the structural integrity of the pipe. And if we raise that pipe up, we wouldn't have enough cover. So we need to find another way to raise that pipe up and still pond water. And the way we might do that is with the control structure. So this is what I'm talking about when I say the depth of water that's sitting in the outflow structure, the overflow structure. So here we go back to this picture where, okay, we do have a perforated pipe in here. It is filling up, but it's not flowing out until the water ponds up to this depth right here. And this is ideal. Never having the water come up through the porous pavement. That could create buoyancy when the rocks are completely inundated. That could create a buoyancy problem. Now, I've heard from Jim Huddleston at the Oregon Asphalt Pavement Association. I don't think I'm saying that exactly right, but he's a smart guy that's been doing porous pavement for a really long time, porous asphalt, and obviously in particular. And he said that the number 3 ballast rock doesn't have buoyancy issues, so it might be okay for the water to come up through the porous pavement, and you won't have any structural problems. But I don't know that, and I'm not going to recommend that. That's up to your engineer to decide. Okay, so that's an outflow control, and then yeah, okay, we got some couple little love notes there. Oh, so we can have a control structure with this pipe here, or we might have a control structure with a weir. So the pipe, if you didn't have, I put this structure uphill And so I've got enough cover on my perforated pipe, and I've got enough cover on my non-perf pipe that's overflowing out here because I happen to be uphill. I've got this depth of soil protecting the pipe. If I had to put this control structure downhill, I might not have enough cover on my outlet pipe, and I might have to use a weir here. And if I used a weir, then I definitely want to make sure that my maintenance staff can still fit their cleaning equipment into both sides of the weir. So that control structure might have to be oversized for them to be able to clean it out. And that's really important that you talk to your maintenance folks, because if they can't get their cleaning equipment down there and someone has asked them to clean it, then they may decide to just take that weir out because they don't know what it does and it's in their way. So communication with your maintenance staff at very early planning stages of a porous pavement is really important. And knowing what kind of equipment they have and what you expect them to do with it all comes into play in the design of your porous pavement. Okay, so now the last step in the user inputs isn't really a user input. It's just a check to make sure that you haven't created impossible situations. So is the outflow elevation above the bottom of the storage rock, that's this thing here, less than or equal to the depth of the storage rock? So if this number is greater than the depth of the storage rock, water's either going to be coming up through the pavement or you've created an impossible situation. So it's just a little check to make sure that you understand what you're doing and that you've entered the numbers correctly. And this should always be true before you move on to look at anything else. So let's look at some things. Let's analyze the calculated values ponding. So the maximum ponding depth that's pulled out of that model that's down here, that Santa Barbara urban hydrograph that's down here, the maximum ponding depth in the storage rock during the storm, during the most intense portion of the 2-year storm, is 1.36 inches. And that includes that takes into account that there's only 40% void ratio in the rock for water to go. So that's quite a low depth of rock, right? 1.36 inches. We're going to in porous pavements in clay, porous asphalts in clay, I've been told to put in 3 inches over 12 inches. But for hydraulic, for the hydraulic design, I need less than 2 inches of rock to store my storm. And then I check to see if the depth of the water left in the storage trenches after 30 hours is nothing, and it is. So that's good. And is the storage trench empty in 30 hours? The storage trench is the rock. It's the storage rock. I'm sorry, that really shouldn't be trench. It should be rock. So is the storage rock empty in 30 hours? Yes. So that's good. But the reason that I said that it might not have to be empty is because if it weren't, there's still a lot of rock left in a 12-inch base rock depth to store rainfall. So just as a little test, because a lot of people are looking at continuous modeling and they're looking at, what if the 25-year storm hits twice, or what if the 2-year storm hits twice in a row? So one day we get the 2-year storm and the next day we get the 2-year storm. Well, the answer is that the size of the storm that could be stored in the rock the next day after 30 hours is 4.8 inches. So we still have, and that's also including the 40% void ratio, but that's the size of the storm. So that's twice as big. Remember, our 2-year storm is 2.5 inches, and that's almost twice as big as our 2-year storm. So that's pretty cool. So we have basically from here we know that 12 inches will work. Actually, we know that 2 inches will work for our base rock. And if we wanted to have a pavement that managed two-year 24-hour storms in a row, we could just up this to 4 inches and move on with our day. So not a whole lot of rock that is needed in this particular situation. The conclusion basically is that for the city of Turner, all stormwater must be kept on site. We're infiltrating the 2-year design storm. It's hydraulically isolated. It's not in a flooded area. Remember, the infiltration rate is what most people would consider very low, 0.1 inches per hour. Porous pavement is suitable for this site. Now, there are other suitability criteria that are not checked in this hydraulic calculator. So you want to check those too, and that's what the decision tree is for. But the conclusion is that this is great. So that's the here's the hydrologic design case study for detention, and we're going to just do another video on that next, so you can go over to, I don't know, wherever you're pulling this out of, wherever you're watching this from. I presume, as I'm making this, that the detention film will be with it as well. The video will be with it as well. So thank you for joining me. I hope you got a lot out of this, and that this will help you move forward with more confidence about using porous pavement. Okay?